Topology is a branch of mathematics which deals with abstract shapes and sizes. Different type of shapes and sizes that we see in topology sometimes become a challenge, a very difficult and a complex things for students and aspirants to learn. What are those abstract shapes and sizes? What is the mathematics concerned with it? What is called those neighborhood points and various other terminologies, which comes as a very complex thing in order to understand, perceive the idea, as well as today's video is to give you a complete pictorial and a graphical understanding of what is topology. In this video, I would try to show you certain figures in hand using certain clay models and other things so that you can understand what those abstract shapes and sizes are. Most importantly, the concept is that why do we need a topology? What is the problem with Euclidean geometry? Why do we need to go from those beautiful Euclidean polygons to those abstract shapes and sizes? That is the prime objective of today's video. I'm going to demonstrate first the Euclidean polygons, and from there, how do we take those into generalized areas, which is called a topological space. I'm also going to explore and make you understand about certain basic concepts of topology, which is called invariance, homeomorphism, bijection. But yes, all those things I will be doing using direct objects, showing you right on this table how things behave. After that, you will see the mathematics becomes much easier. The problem with topology is to perceive in your mind the mental images of those abstract shapes, sizes, how do they bend, how do they deform, and that is why about topological objects. We will start with the mathematics a little bit later, but what we are concerned is about visualizing, seeing those abstract objects right in front of your eyes so that the mathematics becomes much clearer. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this video, Geometry to Topology. So first we will start with geometry. Yes, the basic school level geometry dealing with shapes and sizes of basic geometry, that is what we call Euclidean polygons. The basic idea is that before going into topology, first what we need to understand is that what are the limitations of Euclidean geometry, or we can say the basic geometric sizes, shapes and the polygons, and from there we will go ahead and understand how we are extending those geometrical objects into abstract objects like topology. So first let us go back to our school days and see certain very basic Euclidean polygons, and obviously there is a basic idea why I'm showing you that, and from there how do we move on. So let us go back to my study table, and there we can see what I'm trying to show. Right on my table, as you can see, I have just arranged two isosceles triangles. What I'm trying to show is that when we deal with this kind of a figure, in case of Euclidean geometry, what we are worried about is basically these sides. So this side is possibly equal to this side, and then this side would be equal to this side. So what we are doing specifically is that we are working about the size and the angles of those things. Now let me put forward these two squares also. Again, what we are worried about is that how these squares are being arranged. That means this possible side is equal to this side and this side is equal to this, and the angles of what a square is all about. And from there, if I try to take this type of shapes, for example, if I take this two types of shapes, right? So all these are basically, something which is concerned with the sides. These are also concerned with angles. So if I take this kind of say for example, equilateral triangle, so then obviously what we can say is that this equilateral triangle is not equal to this one, obviously. And this isosceles triangle obviously would not be equal to this one. So what I'm trying to tell is that all these shapes and sizes are basically dealing. Okay, let me show you another shape also. So if I try to move this forward and I put this kind of a shape. Okay, I put this kind of a shape. And I've got all those shapes also over here. So the basic idea of all those shapes are that they are concerned with sides, they're concerned with angles, they're concerned with I would say, different types of perimeters and calculating the areas, etc. Now, also one thing is very important is that, for example, if I'm dealing with this type of a square, for example, and I take a kind of an angle over here, where I'm taking this kind of a shape. So I'm saying that this particular side is equal to this particular side, this one is equal to this one. One thing is very important is that all those geometrical shapes, I mean to say Euclidean shapes, are something very local in nature. Local in nature in the sense that we are concerned about the addition, multiplication, or whatever we do as something which is very local to the surface. We are not moving out of the surface of any of these objects, and we are trying to mention that. So this is what is called the Euclidean polygons, or this particular shape is something which we can call it as a Euclidean space or a vector space. We will come to that later, but this is basically what the geometry, or the, I would say, the Euclidean polygon and the geometry is basically concerned about. All of these shapes, as you can see, either measures the angle, the sides, or the triangles, or the measurement of what I would say the area, perimeter, etc. And all those things are something which are dealing with something very local. That means all those sides and angles, we really don't want to move out of those. But topology actually is not concerned with all those shapes and sizes. Topology is something else. What is that all about? Let us go back and try to understand. So what we saw till now is that a set of polygons, they behave exactly in the same geometrical manner. I mean to say the school level or the Euclidean geometry which we have learned. Also, I tried to show you that these shapes are actually concerned with the angles, the sides, the perimeter, the area, all those things. And also what is important is that all those shapes actually deals with something which is very local in nature. Now, when we tell that this is really local in nature, that means I try to show you that nothing actually, we leave the surface or we try to magnify out from that polygon and deal into that. We will come later into this part of the video when we are talking that these type of objects are very local, and that is why differential geometry is something which is very local in nature, and in order to learn topology, it is called the global structure. So in topology, remember, we cannot apply the rules of calculus or Euclidean geometry, but we have to apply a different kind of a mathematics because we deal with global structures. Now it is the time that we should see the Euclidean polygons at one part and what are the topological objects on the other part and what is the relation between them. So let us go back to my computer desk where a set of beautiful Euclidean polygons as well as beautiful topological shapes are waiting for you. Okay, so welcome back to this my computer table. And now you see these are basically the Euclidean polygons which I showed you, where we are concerned about the lines and the angles, etc. And here you see, let me take it forward to you. Here you see a nice set of all these topological objects. First of all, I would like to express my sincere thanks to my wife for beautifully designing this type of cups. I mean to say this was basically made out of clay, this colored clays, and you see this is absolutely looking like a beautiful coffee cup, and you can have a cup of coffee or tea with that. And also here are beautiful donuts, which if you want you can go ahead and take a bite. It won't be tasty, but anyway, this is a kind of a donut. So what I'm trying to tell over here is that these type of shapes. Now say for example, if I remove all those shapes and I take a kind of a square over here. So this is my square, right? And what I am doing is that I'm trying to take a kind of a topologically equivalent square. So this would break, I'm so sorry for that. So if I take a topologically equivalent kind of a square like this, what is going to happen is that I am not concerned with the sizes or the angles or the sides of this particular, I would say, square. What I am considered is about this kind of a square. Now you can see this is something which you can squeeze around. And although this one and this one looks identical, now for geometry, you would say this one is not equal to this one. So where is my not equal to sign? Yeah. So this one would be not equal to this one. I mean to say geometrically. But a topologist will say that this one if I say, is definitely going to be equal or isomorphic to this one. Now you might say why this is so. Now in order to do that, I would like to demonstrate. Now if I take this kind of a shape, say for example, and if I make it in a kind of a lump like this. Okay, I will take a lump. I will explain you later why I'm making this lump. So I will just try to make it a kind of a lump. So it gets into a kind of a weird shape. It becomes a lump like this. Now obviously this shape which I have just made is not equal to this shape. How it could be possible? I mean to say that is absolutely not done, because this shape looks something weird and this is absolutely square shape. But the idea of topology is to make this kind of a weird shape, so that once we open that shape, technically calling that when we reverse the function, it will go back to this shape. I hope I make myself clear. Of a shape like this. And what I'm trying to do is that I will take this shape. Okay, I will remove this one. I will make a kind of a lump like this. I can make a kind of a lump like this. Now this lump is what? It is an abstract shape. It has got not a shape like this, or a coffee cup, or a torus with 1 hole or 2 holes, or a beautiful square like this. But this is an abstract shape. Now in this abstract shape, if I now move this abstract shape and I will try to make a kind of a nice square, so out of this I can make this looks like a square. It won't be as accurate as my wife, because she's an expert in terms of making art and craft, but I would still try to make it as a square. Right? So now I can say this Euclidean polygon is equal to this kind of a shape. Right? And also I can say that this kind of a triangle, I hope this is visible to you. Let me move it. Yeah. And if I say this kind of a triangle is also equal or isomorphic to this kind of a triangle, this would be equal to or isomorphic to this. Why it would be isomorphic to this? Because again, if I pull it and make it in a kind of a lump and get a kind of an abstract shape, something like this. I make a kind of an abstract shape. Okay, I will put it apart and I will try to take a new lump and I will make a kind of a lump, something like this. Okay, can you call this isosceles triangle equal to this isosceles triangle? For basic Euclidean geometry, it would be a no, because both of the shapes looks different. But again, as you can see, what I can do is that I can make this one absolutely look like this one. So I'll take a shape like this. So eventually it will again come to a isosceles triangle like this. So this one and this one is equal. So that is why, what we tell is that a coffee cup is isomorphic or equal to what we called is a donut. So the coffee cup would be identical or isomorphic to a donut. Now there is a reason for that, because you see this coffee cup has got a hole. This coffee cup has basically got a hole, and the torus also has got a hole. So now we will come to that part of isomorphism, etc. So what we understood right from here, let us remove those things, and I will again try to show you over here, is that any kind of geometrical shapes which are like this one, it might be this one, okay, whatever the shapes that we are taking, it can be a rectangle, it can be a square, it can be a right angle triangle like this, right? Whatever the shapes that I am taking over here, yeah, all these shapes, I mean to say, let me put a kind of a circle right over here. Okay, all these shapes are basically what we call is Euclidean, isn't it? This is Euclidean, or we can say this as a vector space. This is a vector space. That means the normal vectors, the normal Euclidean polygons are behaving over here. Now what I'm going to do is that if I try to extend this one to a kind of a space which is this one, okay, and I will try to put all those meshy abstract shapes all over here. I'll try to put this one, I'll put the donut, I will try to put the square, all those things into this one. Okay, it's clear till now. Now if I try to put all those shapes, all those weird shapes, I can tell that from the Euclidean vector space, I am directly moving to this kind of a space, right? And this one is isomorphic to this one, or it is same as this one, because each of these shapes, this one, this one, this one, this one, this one, and whatever the shapes that actually comes in are all can be used and meant into this. Because this can be actually made into a triangle, this can be actually, changed into a kind of a circle, right? And this can also be made quickly into a kind of a, what I would say, a square. So we can just try to mesh it into a square. It's not going into square, but anyway. So it would take a shape of a square or whatever it likes. So just like those things can be actually formed a triangle like this. Something like a triangle like this. Right? This one, and if I take this one, from the Euclidean space, I'm taking into a different space. I'm not telling you what this space is all about because I will come to that space later. But if I take all those shapes and if I make a kind of a triangle over this, right? And I'm trying to make a triangle over this, these two again are isomorphic to each other. These two are equal to each other. So the basic idea what I tried to show you is that topology is basically concerned more about those abstract shapes. Now why? Because if I use this abstract shape to deduce this kind of an isosceles or whatever Euclidean polygon it is, then I can again deform this shape, okay, to make a kind of a rectangle like this, or I can make a kind of a any shape like this. So if we can study this kind of a lumpy abstract shape, then definitely this shape is going to give rise to all the polygons which we are using over here, and thereby coming to know more about Euclidean vector space. That means each of those things we really don't need to study. We don't need to study this one, this one, this one, this one, this one separately. All we need to study is this kind of a shape. This kind of a shape which will basically give you an understanding of all the Euclidean vector space. This is particularly called a topological space, and it has got certain characteristics which I'm coming to you. But let us go back and try to summarize till now. What we are trying to understand is that any kind of a Euclidean shape which I take as this, if I take any kind of an Euclidean shape like this, how are we trying to expand those shapes in order to get a kind of a lumpy and an abstract shape, something like this? Now the basic idea what I tried to show you is that in geometry we are all concerned about the polygons, whereas in topology what we are concerned about that how these objects can be extended to a lumpy and an abstract space like this, and from there how we can deduce those shapes, so that because this shape, try to understand, this shape is actually consisting of this one, it is also consisting of this one, it is also consisting of this one, and it also consists of this one. So all these shapes are actually inheriting the property of this lumpy surface, which is an abstract space, or a coffee cup which is just like this, as you can see, or maybe a two-hole torus like this. You can see this one. This is a two-hole torus, and if I put another one over here, then what it becomes? It becomes a three-hole torus. You can see this one. Let me put it in front of the camera, this one. So all these holes and all this kind of a surface actually can be made into a kind of a lumpy surface like this. Thanks to my wife, she just made it right now. Now you see this one also consists of this one, and if I try to mend it in a kind of a triangle, it will also consist of this one. That means the entire Euclidean space and the entire Euclidean polygons, the structures, if we can generalize into a kind of a topological object, which is something like this, then what would happen is that that particular object is the only way to study, and we can extend all those things to other geometrical shapes in higher dimensions, and these things will become very, very easy. Not only this, we can also get a kind of a surface which is a triangle. So the basic idea is that the Euclidean vector spaces, Euclidean polygons, once they get extended to this kind of a shape, and again then what I can do is that I can just maybe I can use this one to make another kind of a triangle. So I will just try to so here is the triangle. So now you see this triangle and this triangle is the same. Both of them are the same. You can say this one is this one, this one. But this is a kind of a surface which can be squeezed. Now you see this, if I squeeze it, it becomes a shape like this one. Say for example. Now I take this kind of a shape again to make this kind of a shape. If I can just put it across over here, then possibly not as quick as my wife, but somehow I will be able to make another shape which is something which looks like a triangle. Let me try to make it over here. So I will just put a little bit of squash over here and squash over here, and I will again regain the shape of a triangle. So the basic idea of learning topology is to extending all those Euclidean shapes to a kind of a lumpy surface like this, so that it can be bent, it can be twisted, it can be turned, but definitely it cannot be torn apart. Why? There is a certain reason for that. So I hope this is clear till now. Now we will go back and try to understand a little bit more on how we are moving from a Euclidean polygons to these structures, and what are the features coming up into the next part. Welcome back to my table, where I would like to demonstrate now. Now you see these things which I have just talked about, these are Euclidean polygons, and what we learned is that it can be deduced into this kind of an abstract shape, which is topological shape like this. So now you see what happens if I take a kind of a coffee cup over here. I can take a kind of a two-holed torus over here. I can take a single torus over here, and these are actually what I would say is in a different kind of a space. These things are in a different kind of a space, and all those things are in a different kind of a space. Now the basic idea, what I would now like to show you is that there is a concept which we know as homeomorphism. I will come to the technical definition of homeomorphism a little bit later. But first I would like to show you what actually is homeomorphism. Now we understand that this kind of an isosceles triangle or any Euclidean space is actually equal. I would like to put this shape as equal to this kind of a lumpy surface. Even this kind of a triangle would be equal to another kind of a, say, this kind of a lumpy surface. I will put these things apart. Now why we are doing this? Because from here we can go back to here, and from here we can come back to here. From here we can go back to here, and here we can come back to here. That means if I put it as a kind of a function, say for example, if I put as a function, that means if this function, for example function rectangle, say for example r of f, if this is the rectangular function, that means it can go directly into a topological function, say for example t of f. And also this t of f, which is a topological function, can return back to r of f, that is the rectangle function. Now this is typically a very intuitive idea of what is a homeomorphism. Now say for example, if I take this kind of a, say for example a triangle, or a kind of a, say for example if I make it as a kind of a, this kind of a triangular shape. So when I am trying to make this particular rectangle into this kind of a shape, say for example, let me use the famous example of the coffee cup and the donut. I'm so sorry, I have to deform this beautiful coffee cup. So here you see this is the coffee cup and this is the donut. Now we say that this function, let us say r of f, or the coffee cup function, will go into a topological function and will come back from the topological function back to that function. So in order to do that, what I'm going to do is that I'm going to take this beautiful coffee cup and I will like to retain this hole as intact. Now why it is? Because this hole is equal to this torus hole, and that is why both of them are isomorphic. Now what I would do is that I would try to softly, deform this kind of a shape. And I mean to say this is quite small. So anyway, so it will basically become a kind of a donut. I mean to say, I'm sorry, I have to deform that. So I will use this one rather, and I would like to deform this coffee cup would actually emerge into a kind of a donut like this. So this coffee cup actually contains a kind of a hole, and this hole will be going back to this. Now here is something which is typical in terms of a little bit technical way of homeomorphism. So first of all is that when we take any kind of a shape, first of all is that if I take this kind of a shape, any kind of a shape, so if there are each of those points A, B, C, and then I take another kind of a shape which has got say 1, 2 and 3, it has to be a bijection, or there has to be an onto function. So I put it as bijection, isn't it? Bijection means if I take a kind of a lumpy surface over like this, okay, I'm trying to show you bijection. So if I take a line of a, okay, so for example, I take a kind of a, I make it a kind of a big donut, say for example this one, okay, and okay, let me make it a kind of a abstract shape like this. I think that will be better. So if I take a kind of an abstract shape like this and I put it over here, so this is the abstract shape, okay, and this is the bijection which is happening. This bijection is happening where? This bijection is happening, say for example, over this square. That means if I bend or if I stretch, but I cannot put a hole like this, remember. So if I bend and if I stretch, so when I'm doing that, folding is also, no. So if I bend and stretch and I try to make a kind of a shape like the square, so I'm trying to make a kind of a square shape. Just take a little bit of time to do that. So I will try to use this one as a mold. So anyway, not to waste the time, so you get a kind of a shape of a square. So if this is a square, and if you're turning this to be a square, then there has to be a bijection, remember. It has to be a bijection. That means each of these elements have to map over this element, number one. Second one is that the functions should be smooth. So if I get a function f, it would be smooth. Smooth in the sense, that is what I was trying to tell you, there should not be any break. That means if I take a kind of a topological shape like this, okay, I take a shape like this, I cannot make it this one. So as soon as I try to tear this, the function breaks. So what I can write over here is that if I tear this, tearing not allowed, bending or twisting or stretching, all of these things are allowed. Bending, twisting, stretching, all of these things are allowed. However, we cannot tear things apart. The reason is that the moment we get a kind of a surface and we tear things apart, this function breaks. There is a discontinuous function. So that means if this shape is going into this kind of a shape, first of all, there is a bijection. This is criteria number one. It has to be smooth. That is, this one should be true. And the third one also has to be true. That is, the inverse of the function also has to be smooth. This is an extremely important thing. The inverse of the function also has to be true. That means if I take a kind of a shape which is deformed into from this to this, if you're going, then again from this kind of a shape, I can again get back to this kind of a lumpy surface. That means the moment I am using this one to make it a kind of a this one. This is what the bijection happens. That means this part happens, and it is a one-to-one function. So each element is matching with this. But again, when I'm trying to, again regain it back, this has stumped into a lumpy surface. And now you see, if this lumpy surface again goes back to this one, or maybe this one, or maybe any kind of a shape, so the inverse of the function has to be true. So this is basically the concept of a homeomorphism, that if I take any kind of an abstract shape and if I move on to the another shape, this shape has to have a bijection. That means we can just think it in this way, that say for example, here is a kind of an abstract shape. Let me take the camera a little bit forward. So here is a kind of an abstract shape. Let this shape be this one. And this shape is basically homeomorphing, or you're going into this kind of a shape. This kind of a shape. So if it is doing, then each of this element has to have a bijection or an onto relation, has to have a function which is this one. That means this one goes into this one. And this one, when again it is being regained. So if I get a kind of a square shape over here, and again from this square shape, if I try to get back to this odd lumpy shape, then this the inverse of the function also has to be true. Now there might be a question in your mind that this inverse function is always smooth. So I should have written here as smooth. Now, is there any inverse function which is not a smooth one? Yes, it is, and I would request you to let you know a little bit more in the comment box. So this is the concept of what is called homeomorphism, which is a very central part of topology. There are a lot of mathematics involved in it. So technically, when we try to write homeomorphism, we put it as F, where X maps into Y. So ultimately, what does it mean? It means that this kind of shapes, all these kind of shapes are actually morphing into this one, and again these type of shapes are going back to this. That is why it is in that the function has to be smooth and the inverse of function also has to be smooth. In order to understand what is homeomorphism, which is a concept which is very central to topology, first let us look into the two types of definition. This is a mathematical definition. In the mathematical field of topology, a homeomorphism, also called a topological isomorphism or bicontinuous function, is a bijective and continuous function between topological spaces that has a continuous inverse function. Now, when we read this aloud, we have got certain technical details which we will explain slowly. But what we see is that in the field of topology, homeomorphism is also called topological isomorphism, and it is also called bicontinuous function. Now, it has got two properties. One is a bijective function and another is a continuous function. We will deal with all those things later, but let us look into the simple and a kind of an intuitive definition of homeomorphism. So here it is. It tells that let us imagine two shapes, whatever be the shape it is, and let us think ourselves that it can be squished, stretched, bent and twisted into each other without tearing, without gluing or poking your finger or creating a hole. So they are essentially the same in the eyes of topology, and this relation is called homeomorphism. That means we can get a kind of a rubber band or any kind of a soft kind of a shape which can be stretched, bent, and they should look equally similar. So let us look into an example. If I take a pair of socks, say for example, and if I blow air in it, then I can tell that this sock can be transferred through homeomorphism into a sphere. Now, this looks odd, but I will just explain you what it is. So if you take a socks, I am stretching the socks, I am bending it, I am twisting it, but remember, I am not putting up a finger, I am not poking holes, I am neither tearing. So just try to imagine in your mind that if you get a pair of socks, easy pair of socks where you can blow air, and then definitely it can turn into a sphere. Whereas the same type of socks cannot be turned into a coffee mug, and this is not a homeomorphism. The reason is this, that the coffee mug has got a hole which is the handle,
That means if I turn the socks into a coffee mug, then I have to violate the basic rule of homeomorphism. That means I have to poke a finger and poke a hole, which is not allowed. I have to glue it in order to make another coffee handle which is glued to that, or maybe I have to tear that. This is not an homeomorphism because it uses tearing, gluing, and it is not something very smooth. Whereas on the left hand side, what you see from a sock, if I blow here, it is a homeomorphism because it smoothly transfers into a sphere without violating any rule of homeomorphism. Well, said all those things, let us go back and now let us look practically how we can do homeomorphism with the polygons and other abstract shapes.
Now I hope the concept of topological space and Euclidean space is clear. All these things which resides in a kind of an Euclidean space can be further taken into this kind of a space, and let me write it this as topological space. Now this topological space is basically a kind of an extension, or I would say it is a kind of a generalization of this Euclidean vector space. Because remember all those shapes, this one, this one, this one, and maybe I can just join it to make another kind of a, anyway, so all these shapes, even if I can take all those abstract shapes over here, all those abstract shapes actually are the final class, or we can say it is a final superclass of all those Euclidean space. Now that you have understood that what is a topological space, I think that when you do the mathematics of topological space, things will become easier. Remember, this kind of a triangle is actually this kind of an abstract space. This kind of a rectangle is also this kind of an abstract space. This kind of an isosceles triangle is also coming from this kind of or these kinds of space. So these are topological spaces which actually inherits the property, the Euclidean vector space actually inherits the property of the topological space. So what I can do is that I can now try to draw a kind of a diagram, and I would like to show you in this way. Let me take my black marker so that it becomes easier. So I mean to say right at the top in the basic level is what is called the vector space. So if I write it in this way, this is a vector space. And then it comes the top, which is called the metric space, as you have seen in the demonstration. And then on top of that, what comes is the topological space. So the topological space. Right? So all these things, all these shapes actually resides in the vector space. And all these things, which I'm trying to show you, actually resides in the topological space. So because topological space, these things are actually, bent or, can be taken up into account with this type of surfaces. So obviously these shapes are actually born from this shape, and all those Euclidean space, actually this one actually inherits all the properties of the topological space. And that is the reason we are learning topology, because all those things resides in this kind of a topological space, which has got certain properties, which doesn't have anything like an angle, triangle, etc. Now you see that the moment I draw a kind of a point, like say for example this one A, and I want to measure the distance over here as B, and right is as say for example 5 kilometer, that means what? That means I am specifying basically a metric, and this metric actually falls under the metric space. And I really don't want to do over this. I don't want to take a metric because I am again restricted to what is called a metric space, the definition of metric. So what I do is that I will take this kind of a shape where all those 2 points are actually called neighbors or open set, closed set, those things I will come to that. So the topological space resides right at the top, where all those shapes are actually inheriting the property of the topological space. So this topological space has got certain properties, say for example x, say for example if I write it over here as x, which resides in another, I was so sorry, it should be x which would reside in say for example x. or any kind of a mathematical object which I say actually includes that kind of a space. If I call this as a space. So all these things are basically extension, and we are trying to expand more into topological space so that we can get those abstract objects to study, and from these abstract objects we can define all those vector spaces, all those areas, all those different types of shapes, and it becomes very easier for us to extend it for higher dimensions and understanding. So that is the concept of vector spaces. From here, the Euclidean vector spaces, we go into the topological space. How this topological space basically consists of lumpy surfaces and abstract objects like this, because we are not following this metric, we are following this kind of a system because we want to create a platform independent, metric independent geometrical system, which is only possible when we take this kind of shapes. And here these things do not happen with measurements, etc., but we take care of sets, and that is why set theory is something very fundamental to understand and know about topology.
So what is a topological space?
So I hope till now things are quite clear. So what we achieved and learned is that these Euclidean polygons, what is the need that if we extend it to further abstract shapes, then studying those things will become easier. We don't need to study each and every polygons, the angles, etc. And mostly for higher dimensions and abstract mathematics, these things become very very convenient. So this kind of a coffee cup can be, meshed up, into this kind of a surfaces, and this kind of Euclidean polygons actually are derived from this. Now this is what is basically called a concept of class or object. So if I get a kind of an object which is something like this, and if I can study this kind of a lumpy surface, then all those, I would say the objects which are derived, this one, this one, this one, and even the donut, this one, all of these shapes, will be studied from that particular abstract shape, and it would be easier for us to learn. But what we learned right now is something which is called an abstract vector space, but the general Euclidean polygons are there, and they get transferred into something which is called a topological space. Now, topological space is an important concept in topology, and that is the first chapter which most of the students learn. I hope this kind of an visualization gets you done with the concept of topological space. However, right now coming up the basic idea and the concept of what is a topological space coming up into the next part of our video.
Before going into topological space, first thing we have to take a step back, and we need to understand what is a vector space. So in mathematics and physics, a vector space is a set whose elements, often called vectors, may be added together and are multiplied by numbers called scalars. And this is quite often when we are starting with vectors, definitions, addition, multiplication, different type of operations, we know what is a vector space. So more simplified way, we can say that a set of objects which are called vectors equate with certain operations like addition and scalar multiplication. Let us think of arrows in different directions and lengths. So for example, this is actually a vector space which takes v plus w and it scales and then adds further. This is also a vector space, and this is also a vector space. So overall, this is where a space or an area where all those arrows and lines are residing, and then we add together, then we take something and make it bigger. So all those things which resides in a space is basically called a vector space. So what we can see is that there are primarily few important areas. First is that it is a linear relationship between vectors, obviously the way the vectors operate. The vector addition and scalar multiplication are the key structures, and we can say Euclidean space, space of functions, set of polynomials, all those things resides inside a vector space. So you can see this is basically called an Euclidean space and so on, which has got an x, y, z. It can be three-dimensional and so on. Now the question is that, do we have other spaces also? I mean to say, before going into topology, it is very important to understand, other than vector space, which is a basic root, what are the other spaces we have? So we have something which is called a metric space. We also have a Banach space. We have something which is Minkowski space, that is a flat space which is dealt in Einstein's special theory of relativity. And we have a Hilbert space which is typical to quantum mechanics, and a Sobolev space. Now, what we understand is that all these spaces, metric space, Banach space, Minkowski space, what is the basic idea? I mean to say, all these things reside inside, all these vectors reside inside a space. What is the central idea of the space? Let us first learn into the next part of the video. So when we talk of a mathematical space, what we know is this. That means it should have any kind of a mathematical object. Now you can try to visualize and define what is a mathematical object, but I would say let us imagine any kind of a mathematical object and it should reside inside that space. To make things simpler, for example, small x, I can say it resides in the space X. So here that small x is basically a mathematical object which resides inside a space which is the big X. Similarly, if you take say for example a quantum state or any psi or any wave function, it basically resides inside the Hilbert space. So that means the concept of a space from vector space etc. is that there should be a mathematical object, whatever be it, and it should reside inside that space, and that space will have certain properties which will be the property of that space. So to make things simpler, let us take, for example, there is something which is called a mathematical object, for example, an animal, and it can be subdivided into a mammal, and those mammals can be divided into a monkey and a tiger and a rhinoceros and so on. So those who have learned a little bit of Java or C++, which is called object-oriented programming, you know the concept of this, that how one concept inherits with another. So we have got a kind of a structure called an animal. From there we are getting into another which is a mammal, and there are different types of mammals and different species. So here you see this is an elephant class, and it has got an African bush elephant, we have got African forest elephant. Similarly, Asian elephants can be divided into a Borneo pygmy elephant, it can be an Indian elephant, it can be a Sumatran elephant, or it can be a Sri Lankan elephant. Now what I am trying to tell you is that, for example, all these Indian elephant, Sumatran elephant, etc. are basically the objects which are residing inside this space, and the main space is basically the Asian elephants. Now from here we can go and very well understand the concept of a topological space. So first let us see into this, that we got a kind of an object. Say for example, if you are dealing with an object oriented programming, so we get a class and then we got a subclass. So this is something like that. So we get an object, and from there we deduce and get another object which is called a vehicle, and then we get a car and bike and so on. And again we have got an animal object, and which has got subclasses like monkey, tiger and so on. And then we have got a house which has got a bungalow and then a hut. So one thing we have to be very clear in our understanding, that this hut and the bungalow and the car and the monkey and the tiger actually inherit the property either of the house or of the animal or of the vehicle. That means it inherits the basic class and then the subclass and then so on, and going back to the main object. So topological space is something similar to that. So topological space is actually, is the root class from where we get a vector space, we get a metric space and several other spaces which I have not defined to keep things simple. And this topological space, I would say, is a kind of a space. All other objects inherits its properties. As I will be showing in the later part of the video, that a coffee cup and any triangle or an angle, we can deform that into any kind of a topological objects, and these objects actually resides inside that topological space. So be it a vector, be it a metric, all of them inherit the properties of a topological space. So as you see here, x comma y resides inside the vector space, that is V, and vector space is closed under these operations. That means any operations we do not have to leave the space, everything is within that specific space. So all vector spaces have the property that addition and multiplication occur in a consistent manner. That means we really do not have to leave that kind of a space. So vector spaces generalizes the concept of Euclidean space, which actually gives us an easy way to model physical quantities such as forces, velocity, that have only magnitude but also in direction, etc. But the question that arises now in our mind, is there a guarantee that the addition and multiplication will happen in a similar way if we move out from vector space and we zoom out to another space? Let us look into the next part of the video. We look into what is called a metric space. So metric space is another kind of a space where the basic important thing is that with a notion of distance between elements which is called points. So the distance is measured by a function which is called a metric or a distance function. That means if I move from Geneva to Zurich, and it is whatever be the distance, and if I'm moving from Zurich back to Geneva, the distance won't change. So if I move from X point to Y point and from Y point to X point, the distance would be the same. And this is very, quite observable in our daily phenomena, in our daily world. So that is what it is called metric space, where we are using a kind of a metric and the distant functions, which is D. And that is why I have shown here that it is for X comma Y, which includes in M, which is a set. So metrics on Euclidean spaces are actually calculated using this rule. So metric space has a property of defining any 2 points in that space. So what is the main idea? The main idea is with the concept of distance between them. Let us imagine cities on a map with roads connected to them. So from vector space, what we do is that we move into a metric space where the distance, there is something which is called a D, which is a function, and it measures the notion of 2 points from one point to another. It can be places, cities, locations, countries, whatsoever. Now, here you see the main idea is a set of objects with concepts of distance between them. You can imagine cities on a maps with roads connecting. The focus is that it quantifies closeness and separation between objects. The key is basically the distance function specifying axioms, and examples are Euclidean space with a usual distance, space of strings, etc. Now from here, when we move into topological space, it is definitely a geometric space, but it is more abstract in nature. Why? Because here closeness is defined but cannot necessarily be measured by a numeric distance. So what was there in metric space, what was a numeric distance or a function D, this is not there, and this is measured by closeness. So what we can say more specifically, a topological space is a set whose elements are called points along with an additional structure called topology, and which can be defined as a set of neighborhoods where the point satisfies some axioms, etc. So here you can see it is an abstract space. That means it actually allows for the definition of limits, continuity and connectedness. So what we see is that we move from Euclidean space to metric space, and from metric space to further abstract space, which is called a topological space. So if you ask me that what are the examples of topological space, obviously Euclidean spaces, metric spaces and manifolds are basically examples of topological space. So I hope this makes the point clear that it is actually kind of an abstraction in order to measure distances, but not with any metric, with any distant function, with any point to point, but something which is metric free, I would say platform free, but we will use certain ideas like closeness, continuity, etc. So here you see the main idea is that a set of objects with the notion of openness and closeness of sets capturing the basic, though that means if I want to basically capture the idea of proximity and continuity, I won't use the term of a point or a distance, I would use openness and closeness. Also the qualitative concept of nearness and continuity independent of specific distances, this is very important. And the key structure is, definitely we will see further, the topology is defined by a collection of open sets satisfied by axioms, and any metric space has a natural topology and so on. So now it is time that we see between vector space, metric space and topological space what is actually the relation, and only then we will understand the topological space concept. So the relation is that every vector space can be equipped with a metric via norm, that is the function which defines the distance between vectors or the length, and this metric induces a topology. Every metric space is a topological space. It opens sets are defined using balls, open balls or open neighborhoods, and not every topological space is a metric space. So the first one is true. That means every metric space will be a topological space, but not every topological space is a metric space. Also what we get from here is that vector space actually allows for addition, multiplication and focus on basically linear relationships, whereas metric space quantifies distance between points, enabling concepts like convergence and completeness, and topological space is much more abstract and it focuses on a qualitative notion of openness, closeness, independent of specific distances. So this is basically what is the relation, I would say a little bit of difference, or how vector spaces, metric spaces actually evolve out into a more abstract space which is called topological space, which makes it independent of any metric, any function, any platform, but we can define things much more better and take up to the next level of higher dimensions, etc. This is basically the concept of a topological space.
There might be a question in your mind that is a cube, say for example, this is a nice cube, right? This is a kind of a cube which I take over here. Now, is this cube homeomorphic to a sphere? So you can see this is a nice kind of a sphere with a smiling face, so I'm smiling at you. So this is a kind of a sphere. So the question arises is that is this cube homeomorphic to a sphere? I mean to say, is this, I would say, let us put it this sign, is homeomorphic to this one? And the answer is a very yes. Now let me tell you a little bit intuitively. I won't be able to show you because if I blow air into the cube, or if this cube would have comprised of this kind of a shape, I mean to say if I take this shape and I put it over in a cube, and this shape, this one assumes the kind of a cube, and if I slowly inflate that and slowly turn into this kind of a shape, so essentially it would become kind of a sphere. So the sphere, again, if I take this kind of a weird shape which the sphere has actually regained over here, this one is homeomorphic because this one has been inflated into this kind of a shape, and that is why both of them are homeomorphic to each other. Now try to understand that this kind of a sphere is this one. I mean to say it has taken a shape like this. Let it stay what it is going. Yeah. So it was taken a kind of a shape like this one. This can again be going back from here, and it can again simply go back to a kind of this cube. So this sphere, provided that it is a lumpy surface, something like this, and if I change this one and put it on a kind of a square surface like this is again happening. So that is why cube and a sphere are homeomorphic to each other. Now you see again what I'm trying to explain is that here also three things are taking place. First of all is that the bijection, which is this one, which has got elements like this, and this is the cube, and this is the sphere which has got elements like this. So there is a bijection which is happening. The function which is very continuous, which is from this part to this part, and the inverse of the function is also true because from here I am going to this. So definitely the cube and the sphere is very much, I would say, homeomorphic to each other because it is following all the rules that it is following the onto bijection, it is following the function is smooth, and the inverse of the function is also smooth because from this sphere, if I squish like this or take a different kind of a shape, without tearing, remember, or put out poking a hole, I can get back to this one. That is the reason that a cube and a sphere are homeomorphic to each other. So here you see, the question is that we have got actually three torus. Now if I ask this question that is this torus, I'm going to say this is typically got as one hole, is this homeomorphic to this one, or is this homeomorphic to this one? The answer is no. The answer is no. Now the reason is that you can see that this torus actually has got one hole, and this one has got two holes, and this one has got three holes, and this is what is typically called the study of the genus. So the more we study the holes, I mean to say this one, it has got typical, that means you see now this one, this hole would be equal to that of this one. I mean to say the coffee cup. So this one, I'm sorry, it has broken down. So this one would be, similar to this one. So this would be, I would say, isomorphic to this one because it has got a single hole. But this one won't be isomorphic to this one because it has got two holes. And this one is also not isomorphic, or I would say is not homeomorphic to this one. So if this one, I mean, the torus with one hole is, I would say, homeomorphic to one particular, this coffee cup, which has got a kind of a handle like this, or maybe I take a bigger coffee cup to show you this one. Okay, It has got a handle like this one. So this one and this one would be the same. However, this one won't be equal to same because it has got only one hole, and this is out of question because it has got 3 holes. So that means when we are studying the concept of the genus, what we are worried about, if we take any kind of an object which has got one hole, what we would try to find out is that are there other objects which has got one hole, If this coffee cup or any other objects which is similar to this has got a one hole, that means this one is homeomorphic to this, provided the bijection and all those factors comes true. And this is because this one hole coffee cup can be, as I showed you, can be bent, turned, etc. into a kind of a torus like this. Remember, this hole will be the same. I mean to say it would be identical, because even if I change this one, right, it would be the same thing like this. I cannot deform this particular hole, and same happens with this one and this one. So torus with one hole is not homeomorphic to this, is not homeomorphic to this, but this one would be equal to this one. That means the study of genus again becomes very useful in terms of identifying which object which has got hole. So if I can categorize this kind of object into a similar kind of a I would say set, or a kind of an area where all these objects are placed over here, then we can go and further study. Similarly, and I try to make it just as clear as possible. And from this rubber band, if I, change it, you see it takes the shape of a figure 8. Can you see this one? This is almost the shape of a figure 8. That means this is actually the concept of immersion, which is not, I'm going to explain it right in this video. So if this one actually bends, the circle or the basic idea of this rubber band, which is a kind of a, say for example, a circle, it will remain the same. That is what it is called topological invariant. And when this changes and it bends and it cross each other in form of forming a kind of a figure 8, then what happens is that there is a kind of a cross. But when I revert back, that means when the inverse function I come, the invariant or the properties of this circle, for example, remains the same. That means any kind of a shape that I take, say for example, if I take any kind of a shape, and if I move those shapes, say for example, into this particular area. So if I take this kind of a shape and then I move into this, and I take this kind of a shape and move into this, and I get this kind of a shape and I move into this, or I can take this kind of a shape and move into this. So what is happening over here, that although these type of shapes are being changed over to here, here and here through homeomorphism, bending, twisting, whatever, but the basic idea that when this particular shape is coming back to this particular shape, the topological invariant is maintained. That means the basic properties of all these shapes, whether it is being turned, twisted or bent into all these type of shapes, remains invariant. That is what is called the topological invariant, and that is the basic objective of the study. Because remember, when we draw a kind of a vector area, which we already have done, this is some kind of a similar thing. So if I draw a kind of a vector over here and I coordinate and I show a vector, say for example v over here, and when I turn it, say for example this is the x and this is the y, I'm not drawing the z. So if I turn this into this one, and if I turn this into this one, so this is the x and this is the y, so it gets turned up. Understand that the vector v will be invariant. So this is what is called the vector v is invariant. Although the components of the vector will change, because when I will measure this, the x-axis and the y-axis, the components of the vector is going to change. Similar things happen over here when we take this kind of a surface, or this kind of a messy, kind of a lumpy surface, squishy surface, and we try to, deform and do all the homeomorphism and get into shapes like this one. So when I pull back this shape back into this, the structure or the topological invariance remains the same. Just in this case, as the vector remains the same, here also the topological invariance remains the same. So that's all for today's video. I just tried to show you, what are those implications and meanings of those shapes. So you get a kind of a, box like this. and then you try to use this kind of a lumpy surface over here, and then you try to get it back into this kind of a sphere. So sphere again, and this one would be topologically they are the same, or they undergoes a homeomorphism. But remember, if I take a kind of a ball like this, that is a sphere, and I take a cup like this won't be homeomorphic because this has got a hole. And because this has got a hole, I cannot, make or put a pointer or poke something in order to make this sphere a kind of a hole. So that is why you see that a coffee cup and a sphere won't be homeomorphic. I hope you like this video, the entire idea. So, drawing a lot of shapes, etc. actually takes a lot of time. But anyway, what the basic idea was that how do we extend from Euclidean polygons to topological spaces? What is actually a topological space? How we do the homeomorphism of using this kind of lumps and in order to generate this kind of shapes. And most importantly, what is bijection, and the function and the inverse function is also true. However, there are some more concepts which are called immersion, embedding, a lot of other topological concepts. So in the next video, what I will try to do is that I will try to take a few more concepts in topology, and using this kind of similar shapes and sizes, I would like to demonstrate. Now, as you see that because all these shapes, all these, they fall under certain category. So automatically the concept of sets come in. Because we are not using metric spaces, we are not using distance, etc. But we want to make a totally different kind of an idea where it is all, I would say, metric independent, platform independent, but it will have one kind of a typical super object or a class of object from which we can actually derive the different kinds of objects. So if this is an abstract shape, say for example, and if we know that this triangle or this square or this kind of a rectangle is actually taken from these shapes, then we can study the structure of these shapes, and then we can extrapolate and we can find out different properties doing that. So for this kind of a lumpy surface where we are actually not using any points, any metric, any distance, any angle, all those things, they becomes very true. And this is why it is called the concept of continuity, divergence, etc. Remember that even in topology, we are unable to use what is called a calculus, because again calculus and differential geometry is very local. Topology is zooming out and taking much broader scale. Thank you very much for watching this video. Please put up your comment and let me know how this video you liked it, and whether your concept of topology, the abstract shapes, they are homeomorphing and they are changing into different shapes, and how the mathematics works out, vector space, Euclidean, and then into topological space. Are these abstract concepts very clear or not? Please do let me know in the comment box, and see you soon in Physics for Students with yet another interesting video. Till then, goodbye.